Hello and welcome to another video on optimization. Today we will see optimization problems under uncertainty. What happens when we consider a system that is affected by uncertainty? What happens to the optimization problem? How can we handle an optimization problem that is affected by uncertainty? So what is optimization under uncertainty? Optimization that accounts for unknown or variable factors. Why is it important to consider uncertainty in optimization? Considering uncertainty helps us to make robust, risk-aware decisions that perform well under varying scenarios. So even if a problem is affected by uncertainty, the decisions that we take should perform well even under uncertainty. So every real world problem is affected by some kind of uncertainty. It may be model uncertainty or the uncertainty due to measurement errors. So there are different ways the real world systems are affected by uncertainty. So in the optimization problem also, we need to take into account this uncertainty so that the decision that we take are appropriate and that will take into account this uncertainty and perform well under varying different scenarios. Some of the practical examples are stock market, supply chain disruptions, and energy systems. Say, for example, goods are traveling from one location to another location. There is a possibility that can be disruptions in that supply chain. It can be environmental, such as tornado or rainfall. There can be other disruptions in the supply chain due to the health issues or environmental issues due to COVID-19, etc. So all these, in many cases, we may not be able to consider those uncertainty, but there are cases where we could take into account and we could generate a robust and risk-aware decisions that could perform well in various scenarios. What are the sources of uncertainty in optimization? There are data uncertainty, example, demand fluctuations, noise measurements. So the data that we get at our hand has some uncertainty, has some variable factor in it. So that is data uncertainty. In model uncertainty, we may not know proper relationship between different variables of the system. So the relationship between state variables, control and state variables, there can be many approximations in those. We start modeling by physical relationships, but by first principle rules, but there can be models which are black box or gray box models. So those are approximate models. So those model uncertainties will affect the will cause uncertainty in the system. Decision uncertainty. So there can be unpredictable external factors that affect the system. So those also will cause uncertainty in the system. So this optimization under uncertainty is done various ways. Two popular way of handling uncertainty in optimization are robust optimization and chance constraint optimization. In robust optimization, what we do is we consider the worst case scenario. So the worst case scenario is handled in robust optimization, and in chance constraint optimization, we set some acceptable risk level. So it is not true that we will handle all the uncertainty, but most of the cases, maybe 90% or 95% cases, this uncertainty can be handled. We will see an example. A city manages a water reservoir and needs to decide how much water to release daily while ensuring enough water remains for future needs. However, future rainfall is uncertain. So here the uncertain factor is rainfall. So rainfall fills the reservoir, and this reservoir is distributing water to daily needs of the city. So we will see how this is handled in a robust optimization fashion and chance constraint optimization fashion. So before even beginning with robust or chance constraint approach, the first simple and easy method is to take the expected values or the average values. So we will consider the problem with uncertainty to a deterministic problem. where we will take the expected value of the uncertainty as a single value and then solve using deterministic fashion. So here the approach is the city models the rainfall as a random variable and optimizes the expected water level over time. On an average, how much water should be released to maximize water supply without running out? So here they use the expected values of the uncertain parameter. So the expected value will be only a single value, expectation of that random variable. So that will be a single value that will be substituted in the optimization problem and then solve it deterministically. So the ultimate aim here is to optimizing the expected performance. Now we will see how in robust optimization the uncertainty is handled. The approach here is that city assumes the worst possible drought scenario within a known range of uncertainty and optimizes the water release to be safe under all cases. How much water should be released to ensure we never run out, even if the lowest predicted rainfall occurs. So what they focus on the worst case guarantees, the worst case scenario. So when we consider the worst case scenario and take a decision, it will ensure that we have a feasible solution under all possible realization. For all possible uncertain realization, we will have a feasible solution since we had taken the worst possible case into account. So this is a worst case approach, but it is a conservative approach. The decision that we take is very conservative decision. So here in this example, what we have seen, they are assuming the worst drought, lowest predicted rainfall. So that may not happen always. So they will release only the minimum amount of water. That means they are very conservatively deciding based on the worst case scenario. So robust optimization takes the worst case uncertainty into account while choosing the decision variables. In chance constraint approach, the city ensures that the reservoir does not run dry with at least 95% probability, allowing rare cases where it might. So how much water can we release while ensuring that reservoir remains above 95% critical level at least 95% of the time? So here there is a probability considered. So we are taking the decision such a way that 95% of the uncertain values it is satisfied. For the rest 5% it is not satisfied, may or may not be satisfied. So we are taking a risk there. So the key feature here is that constraints hold most of the time, but not always. So there is some slight risk, like 5% in this case. So they are considering a probabilistic feasibility. This chance constraint approach is not as conservative as robust. In fact, it is more efficient to consider this chance constraint approach because always the worst case scenario will occur, and the chance of this worst case scenario being occurrent is very low. Hence, it is very efficient to consider this chance constraint approach. What are the challenges and trade-offs that we need to consider while considering an optimization problem under uncertainty? The first and foremost, we need to computation complexity. While handling large-scale problems, the computation complexity plays a vital role. When considering the chance constraint approach, the computation complexity is slightly higher compared to the robust approach. Another factor that we need to take into consideration is conservatism versus performance. Over robust solution may be inefficient to consider. As I mentioned earlier, not always the worst case situation happens. So if we take our decision only in the worst case situation, it will work for all other cases, but still the solution that we get, the decision variable that we take is very conservative. It is overly conservative solution. And that may be an inefficient way of doing it. Data availability needs for accurate probabilistic models. So in chance constraint optimization, this uncertainty needs to be accurately modeled. So the model of the uncertainty may not be accurate. So that will affect our optimization problem also. So data availability is vital in case of formulating a problem in optimization under uncertainty. So we will see more about these techniques in the future videos. Thank you.